So that's the topic for today. It's capacitors, which is a very great way to end static electricity because capacitors are um, are something that we talk a lot about in circuits. Let me just erase the board so that you guys can see better. All right. And essentially, what capacitors are two parallel plates separated by some substance called a dielectric. Right? And we'll talk about why this is important. Heard of the term capacitor before? Yeah, maybe some of you. This thing here, this blue thing that shows up, that blue thing, you've definitely seen something that looks like that before, right? Essentially, these are parallel plates, and you're asking yourself, well, what is it? Why is it in a cylinder, and how are they parallel plates? And it's pretty cool the way they invented this stuff. It's pretty ingenious. I'll tell you about how that's built a little bit later on. But what's important here is that capacitors are devices that can hold a charge because there is an electric field on them. So Benjamin Franklin demonstrated this capacitor phenomenon. He didn't really talk about it or describe it, but it was a man named Michael Faraday um, who actually described it for the first time. And Faraday, do you guys remember? Does that name ring a bell for something? Maybe in a grade 10 science class, perhaps. Farads? No, you never heard about farads? No. Okay. Well, he came up with a unit of measure called farads, right? And it's named after him. And we're going to be using that a lot because it's the basis of what capacitance is measured in. And essentially, to give you a little bit of the anatomy of a capacitor, it's two parallel plates, and the parallel plates have this area A, which is very important. They're separated by a distance d, and there is a substance called a dielectric in between them. Okay, and this dielectric has to be an insulator. Super duper important that there is an insulator in between. Okay, the better the insulator, the better the capacitor. Capacitance is how much charge a parallel plate capacitor can hold. Okay, I'll explain to you. I'm gonna have I have like 3 videos to show you guys. We don't have to watch all of them, but I'll show you how they work exactly. But essentially, you have to take my word for it for now that these two parallel plates can hold charge. A certain amount of charges can get stored into it. What else stores charge that you guys might know about? Very common in your lives. Batteries, exactly. Batteries store charge, and so do capacitors. And capacitors can be used as a power source for certain things. Um, you guys have seen a camera flash, that's a capacitor. You guys have seen defibrillators, those are capacitors. You've seen lightning strikes, that's a capacitor. Yep. Yeah. It's not a small amount of or a big amount of voltage, but it's a small amount or big amount of charge. And your answer is yes. And the answer is yes. It's either it's fast and like a capacitor, or short term or long term like a battery. Okay, and there's a way to measure how much charge a capacitor can has a capacity, and you can measure its capacitance by looking at the ability of the capacitor itself, which we know is described by the area, the distance between the two, the value of the dielectric, and the voltage applied to that capacitor. Okay, so if there's a voltage and a capacitance, you can figure out the charge. All right. And we also know that because these are that these are parallel plates, that we know that its electric field is equal to this. We just derived that, and remember, whoops, go back. And we remember that Q divided by A is the same thing as epsilon as sigma. All right. We could only do this thing because of how the electric field ends up being between these two parallel plates. Capacitors are hugely important, so we just I'd like you guys to gain an appreciation for how valuable they are. Again, there's a video on that stuff later. I mentioned to you that capacitance, or the amount of charge being able to be held by a capacitor. So let's describe that. So capacitance is the amount of charge able to be held by a capacitor morning. And capacitance is measured in a unit called farads. F. Yeah, these are the units. Yep. So for this formula here, that is for an infinitely large plate and us taking a Gaussian surface of a cylinder. All right. Is it derivative? No, it's not derivative. It's basically like an estimation of the edge fields not contributing to the center. So if you were to put these parallel plates so far apart, then what's going to happen? You have an electric field of 0, or essentially you can treat, if I take this room and I look at it from this ceiling, it looks like a flat surface, right? If I look at this room from the moon, it looks like what? It looks like a dot. It looks like nothing or a dot, all right? And so if the two plates are really far apart, then you can treat each plate as a dot charge. And we know how to do that. It's different, the calculation, and the electric field is going to be really, really low in between. So these two parallel plates have to be relatively close to each other in order to be able to ignore the outer edges, and in order for the electric field between them to not be 0. Yeah. The area of one surface is enough for this calculation. Yeah, they should be the same. They should be the same area. No, it's not 2 times 8. It's 1 times 8. Okay. Okay, so what affects this capacitance? What affects it so that this capacitor can hold charge or cannot hold charge? Well, there is this thing called permittivity, material permittivity. Please don't get that confused with this constant here, which is called permittivity of free space. Those are two different things. All right, so K is material permittivity. I'm going to write that here. And also don't get confused with that other constant, the Coulomb's law constant. This is not the same thing. It's still K, yeah. That's that's the nature of the insulator in between the parallel plates, all right? If it insulates or not, yeah, yeah. So to give you an idea, air has a material permittivity of 1, okay? So K air is equal to 1. It's kind of like index of refraction in the sense that it doesn't have any units. A is the area of the plates, and D is the distance between them. So what happens if you increase the distance between the two plates? Is the capacitance going to go up or down? Going to go down, and if you decrease them and bring them really close together, the capacitance goes up. If you increase the area, is the capacitance going to go up or down? Up. Okay. The electric field will go down, but the capacitance will go up. Yes. Yeah, exactly. That's this one here. Okay. Yeah. So if we go back, the A in the, is in the denominator. So if you increase the denominator, electric field goes down. Well, the charge density, if the number of charges stays constant and you increase the area, then your charge density goes down. Yeah. All right. Here it is, some of the more simple capacitors. What you'll see inside here is parallel plates. So, I mean, I can't really draw. My drawing is not good enough. But imagine in this, two circular parallel plates, really small, close to each other. They're really super close. They're separated by probably ceramic or some really amazing insulator. And and the area would be the area of this kind of device here. Okay, pretty simple. This one is a bit more complicated. This letter C is a bit more complicated because of how the capacitor was made, and it's actually quite ingenious. Let me show you a picture. I'll come back to it. So those capacitors are made like this. So the two conductive electric plates are malleable, and they're separated by a malleable insulator, and they're rolled around together so that they're parallel at all points, and then they're shoved into this cylindrical shaped thing. So what you have to be careful for is that these capacitors can actually hold a charge despite there being, what happens is you charge them. So you know when you go, yeah, those paddles, you press the button and you hear it go, doo, that is the capacitor being charged. The charge is entering the electric field of the capacitor. And then if you remove the electric source, if you unplug it, that's still there. That charge is still there. So a lot of these devices that have capacitors, they still hold charges in their capacitors. A lot of them are for like surge protectors. You guys know what surge protectors are? No? Surge protectors are, so let's say you have a very sensitive electronic device that if you get a surge from, let's say, a power storm or something like that, and the power gets cut out and you don't want this power to just get shut down and you want it to get shut down slowly, a capacitor is going to be built into it so that when the power shuts down, it's getting volts, it's getting energy from the capacitor, and it can slowly shut itself off the proper way. Then it doesn't just cut out immediately. A lot of the more sophisticated stuff has that, but like your toasters, for example, might not because it's not necessary that it gets shut down properly. The insulating material inside the dielectric that I talked to you guys about has to be polarizable. All right, and this is, if you look at it, this is the parallel plates with no voltage across it, and here you place a voltage across it, so there's a positive charge at the top, a negative charge at the bottom, and the insulating material in between is polarized in the sense that you have all the negative charges aligning with the positive end, and the positive charges aligning with the negative end, okay? And that's really, really, really important. So far, so good? The dielectric makes it so that you need less voltage to achieve the same amount of charge. Okay, so you're getting the same capacitance, but it's requiring you less volts to do that. And that's what's important about that dielectric that's written right here. So if we had an example, we have our two equations that we talked about. We said Q is equal to capacitance multiplied by voltage. And we have that capacitance is equal to the material permittivity multiplied by area divided by the distance between them multiplied by epsilon naught, right? So if we had these two equations and we're trying to solve this, so Science Fair Radio uses a homemade capacitor made of two 35 by 35 centimeter sheets of aluminum foil separated by a 0.25 millimeter thick sheet of paper that has a dielectric value of 3.7. What is the capacitance of the capacitor? So you guys should be able to solve that. I'll give you guys a couple minutes. Try it out. So essentially the parallel plates are going to sandwich this paper. So how well could it sandwich provided that thickness? So what's the difference between it? What's the distance between the two plates if there's something of that thickness in between it? The answer is right here and right here. Yep. It's the permittivity of the material. In this case, the permittivity is here. That's the K in the, yeah. That determines how well insulating your material needs to be. So remember your SI units. Capacitance is equal to 3.7 multiplied by the area, which is 0.37 squared. What's that? Oh, not 37, right? Divided by the distance between the two, which is 0.00025 meters. Multiplied by epsilon naught, 8.85 times 10 to the negative 12, times 10 to the negative 12, right? There's it. Negative 12. And that should give you a measure in farads. 1.6 times 10 to the negative 8 farads. And that's correct. That's the answer that we got here. All right, that's how good this capacitor is. So remember, capacitance is a measure of how good your capacitor is, how much charge it can hold. Something that has a capacitance of 1 farad is dangerous, like seriously dangerous to your health. You don't want to be in contact with that. Most capacitance, like let's say between you and a door handle, something like that, when you get a discharge, it's going to be in the less than nanofarad. Okay, 1 farad is deadly. Yeah, just like 1 coulomb is deadly. All right, let's try a second example. This one's a bit trickier. So 30 nanofarad homemade capacitor is connected to a 25 volt battery. How many charges are held on the capacitor? So remember again that Q is equal to C times V, and that C is equal to KA over G times epsilon. What's the difference if I ask you what is the charge and how many charges? There's 2 different questions there. Practice this for your test because you don't want to lose marks for nothing. So what is the charge versus how many charges? What is the difference between those 2 statements? Okay. All right, we'll keep working on it. Yep. Yep. So letter A is pretty easy. You do Q is equal to C times V. That's going to give you the charge. Then you divide it by the elemental charge to figure out, oops, sorry. to figure out the number of charges. B, what would you do in B? What's going on in B? Anais? Right, you don't have an area or a distance, but it's the same capacitor. So therefore, it's the same area and the same distance. So that means that the capacitance, other than the dielectric, is staying the same, right? And your permittivity is the only thing that's changing. So your capacitance is going to go up by a factor of 81, right? So let's say it held 1 charge in problem A. If you enter that dielectric, it's going to hold 81 charges instead, right? It's the same capacitor in letter A and B. The area and the distance do not change. Shani, did I answer your question? I don't know. That's just Q is equal to C times V. So there's C, there's V. Q is not the answer. Q is the charge, and then you need to figure out the number of charges. Then you divide that one by 1.6 times 10 to the negative, what's the number? 19, negative 19. Yeah, same thing. Exactly. Yeah. So this would mean that capacitor can hold 81 times more charges. Yep. If you only had C, you did not have the voltage at all? No, then you don't have enough information. You can say that if you only had C, and if I told you 81 times that, you can just say the capacitor now has 81 times more charges, right? But you won't be able to quantify exactly how many charges, because that'll depend on the voltage. All right, the third one's kind of hard. So if the capacitor was disconnected from the battery before the dielectric was inserted, what would happen to, 1, the amount of charges, and 2, to the voltage? All right, I'm not going to answer that now. We're going to watch a video, and then we're going to come back and answer this. Okay? So I have 3 for you. Let's watch this one first. They're all kind of...
as long as those 3 things are true, then we can represent the electron.
Okay, so this guy's called Bozeman Science. He's a physics teacher that does something called a flipped classroom, which means that he teaches everything from at home. The students, they just watch his videos and they come to class and all they do is solve problems. It's a lot more homework for you guys, but it ends up working in the long term. It's something that I have always wanted to do, but students never want to do. One day, I'll get my way. But anyways, okay, so this guy, Bozeman Science, he's going to explain something. He's really good at explaining. He's one of the people that I recommended on that document that I showed you at the beginning of class. You should definitely take a look at his videos. This one is linked there as well. And so just do a search. The video is 8.5 minutes. You guys okay with 8.5 minutes of talking? That's just the first one. There's 2 more after that, and I think they're both longer than this one. That's okay. But I really do think that they can help you guys.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 30. It's on the electric field of parallel plates. And we've already learned so far that the electric field will look like this. It'll go from the positive to the negative, but we haven't got into the details of that. Before we get there, let me give you a quick application of this. In biology, we use gel electrophoresis. And what you do is create an electric field across this gel, and then you can add DNA fragments to it. So we're going to put DNA fragments in right here. And what happens is they'll respond to that electric field. And DNA has a negative charge, and so what they're going to do is they're going to migrate across that electric field. Now what's interesting is the DNA is each going to have a different size, and so the small fragments will be able to move really, really far, and the larger fragments won't move as far, and so we can create a DNA fingerprint. And so if we have two parallel plates, and we make sure that they're oppositely charged, and we also make sure that that charge is uniformly distributed, and we also make sure that we're really far from the edge, as long as those three things are true, then we can represent the electric field like this. And if that's our electric field, we know that the electric field strength is going to act perpendicular to those plates, and it's also going to be constant or uniform throughout. In other words, no matter where you test the electric field inside here, it's going to give you the same value. It's going to be the same direction, and it's always going to be the same size. Now, how do you figure out the electric field strength here? There's a couple of ways we could do it. We could look at the voltage across that gap, and then the displacement, or R, across the gap, and that would tell us the electric field strength. Or we could just use the charge of the plates and the area of those individual plates, and that's going to give us the electric field strength as well. The last thing you should pick up from this video is what happens if we add a charged particle to this electric field. What happens if I take a proton, for example, and I give it a velocity in the horizontal right here? Can you predict what's going to happen as it enters into the electric field? Remember, positive charges are going to follow the electric field, and so watch what happens as we let it go. So it bends like that, but you can see that it continues to have the same velocity in the horizontal. What we're really doing is changing it in the vertical, and so this works exactly like projectile motion. However, projectile motion, that electric field is going to be the gravitational field. So can you predict what will happen if I take a negative charge and add it in that direction? Which way do you think it's going to go? And like that. It looks just like throwing a baseball, that parabolic curve, because it's the same thing. It's moving horizontally, and that's not affected by that change in the force in the vertical. So in order to look at the electric field of parallel plates, it's sometimes easier to look at them individually. So if we look at the positive plate and we draw the electric field lines, it's going to look like that. It's all moving out from the plate. And now if we draw the negative, it's going to be moving towards the plate. And so if I now simply just combine those two, it's going to look like this. Now you can see on the edge, in order to figure out which way they're going, we'd have to do some vector addition. And so we're just going to say that we're really far from the edge. And then you can also see up here and down here that that net electric field, since it's so close together in relation to the overall length of this plate, that it's also a net of 0. The only place where they're going in the same direction is going to be in the middle. And so we can treat that as our net electric field, that uniform electric field on the inside. And if we want to figure out what the electric field strength is, we could use the charge and the area of those plates. And so if we use this equation, what we've got here is the electric field strength is equal to Q, which is going to be the charge, divided by the permittivity of free space. Remember, that is a constant, and so that's going to offer resistance to an electric field. And then we're going to multiply that times area. And so if we increase the charge on the top, then we're going to increase the electric field strength. And if we decrease the area, then we're going to increase electric field strength. So let me kind of walk you through that in a PHET simulation. We've got here our two plates, and we can add charge to that. And the charge will show up right here, and then we can measure the electric field down below. And so what we're looking at is what happens when we increase Q, and then what happens when we increase or change A. And so what we're going to do is put our electric field sensor right in the middle, so you can see there's no electric field strength. And as we add charge to it, watch what happens to our electric field. It's getting greater. And so what we could do is at this point, we could solve for E. If I add more charge, or I add more of the negative charge, you can see I'm increasing that electric field strength. Now what happens if we change the plate area? As we decrease the plate area, you can see that we're increasing the electric field strength. Because it's in the denominator, if we decrease it, we increase the electric field strength. If we increase the area, what we're doing is decreasing the electric field strength. And so it's a really nice relationship between charge and the area of the plates, and then the electric field strength. But we could also go at it in a different direction. We could look at the voltage or the potential across that gap, and then the distance or the displacement between the two. Now voltage, remember, is the amount of work that we would have to do to move a positive charge against that electric field. So that's going to be the voltage. And then R is going to represent the displacement or the distance between those two plates. And so here is our equation. Again, if we increase the voltage, we're going to increase the electric field. And if we decrease that displacement, we're going to increase the electric field as well. And so we've got another little simulation right here. So what I've done is I've got the electric field sensor in the middle, and now we've got a voltmeter. And so now as I add voltage, I'm increasing the volts. Watch what happens to my electric field. So an increase in the voltage as we move it up to 1.5 volts is going to increase that electric field. And we could move it in the opposite direction, and we're going to have the same thing. The more voltage you have, the more potential difference you have, then the greater that electric field strength is. But watch what happens when we decrease the distance between the two. So as we make it closer and closer together, we're increasing the electric field. Since R is in the denominator, by decreasing it, we're actually increasing the electric field strength. Last thing you really have to understand is how motion of particles inside an electric field is similar to motion of objects on our planet. So imagine I were to roll a ball across a table, and at the moment it goes off the edge of the table, we take a similar ball and we drop it from a similar height. You've maybe done this before. Which one's going to hit the ground first? Well, the right answer is that they're both going to hit the ground at the same time. And the reason why is that they're both in a gravitational field. And so even though this one is moving horizontally, that doesn't affect the force and therefore the acceleration in the vertical. They're both going to fall at the same rate. Now charged particles work the same way inside an electric field. And so if this is our electric field, what happens if we add a positive charge to it? It's going to follow those electric field lines. But what happens if we shoot a positive, let's say a proton, horizontally into the electric field? It's just like that ball rolling off the table. It's going to accelerate down at the same rate as that point charge did to begin with. Or if we had a negative charge, and that negative charge we shoot into the electric field like this, it's going to do not what balls do on our planet. It's going to actually go against the field. And that's what's cool about electromagnetism. It's going to go in that direction. But it's still following this similar path as projectile motion because we have this set electric field. And so did you learn to create representations of the electric field between parallel plates? Again, we have to be far enough from the edge and the plates have to be close enough together. Did you learn to calculate the magnitude and determine the direction of the field? Again, we could use voltage and displacement or separation, or we could use charge and area. And then finally, did you learn to represent the motion of electrically charged particles inside an electric field, similar to that of...
We'll stop that there. And we'll go to the next one.
Volts. Typically.
Have you guys ever heard her videos? She talks super duper fast. I'll show you that one last, but I actually don't want to let you see this one.
Volts. Typically, capacitance values are very...
No, that's not the one. Is it the same video now? No.
Volts. Typically, capacitance values are very...
Hey, give me a moment. I'm just going to find the other video. I'm going to open my YouTube history. I'm going to turn that off. I watch a lot of Game of Thrones videos.
plate until both plates become back again electrically neutral. So that's the basic working principle.
Okay, here we go.
Hello, Dan Adilkowski here from howtomechatronics.com. In this tutorial we will learn what capacitor is, how it works, and take a look at some basic application examples. There is almost no circuit which doesn't have a capacitor on it, and along with resistors and inductors, they are the basic passive components that we use in electronics. A capacitor is a device capable of storing energy in a form of electric charge. Compared to a same size battery, a capacitor can store much smaller amount of energy, around 10,000 times smaller, but useful enough for so many circuit designs. A capacitor is constructed out of two metal plates, separated by an insulating material called dielectric. The plates are conductive and they are usually made of aluminum or other metals, while the dielectric can be made of any kind of insulating material, such as paper, glass, ceramic, or anything that obstructs the flow of the current. The capacitance of a capacitor, measured in farads, is directly proportional to the surface area of the two plates, as well as the permittivity of the dielectric, while the smaller the distance between the plates, the greater the capacitance. That being said, now let's take a look how a capacitor works. First, we can note that a metal typically has an equal amount of positively and negatively charged particles, which means it's electrically neutral. If we connect a power source or a battery to the metal plates of the capacitors, a current will try to flow, or the electrons from the plate connected to the positive lead of the battery will start moving to the plate connected to the negative lead of the battery. However, because of the dielectric between the plates, the electrons won't be able to pass through the capacitor, so they will start accumulating on the plate. After a certain number of electrons accumulated on the plate, the battery will have insufficient energy to push any new electrons to enter the plate because of the repulsion of those electrons which are already there. At this point, the capacitor is actually fully charged. The first plate has developed a net negative charge and the second plate has developed an equal net positive charge, creating an electric field with an attractive force between them, which holds the charge of the capacitor. Let's take a look how the dielectric can increase the capacitance of a capacitor. A dielectric contains molecules that are polar, which means that they can change their orientation based on the charges of the two plates. So, the molecules align themselves with the electric field in such a way enabling more electrons to be attracted to the negative plate, while repelling more electrons out of the positive plate. So, once the capacitor is fully charged, if we remove the battery, it will hold the electric charge for a long time, acting as energy storage. Now, if we shorten the two ends of the capacitor through a load, a current will start flowing through the load. The accumulated electrons from the first plate will start moving to the second plate until both plates become back again electrically neutral. So that's the basic working principle of a capacitor, and now let's take a look at some application examples. Decoupling capacitors or bypass capacitors are a typical example. Decoupling capacitors are often used along with integrated circuits and they are placed between the power source and the ground of the IC. Their job is to filter any noise in the power supply, like voltage ripples which occur when the power supply for a very short period of time drops its voltage, or when a portion of a circuit is switched causing fluctuations in the power supply. At that moment, when the voltage drop occurs, the capacitor will temporarily act as a power supply, bypassing the main power supply. Another typical examples are capacitors used in DC adapters. For converting the AC voltage into a DC voltage, a diode rectifier is usually used, but without the help of capacitors, it won't be able to do the job. The output of a rectifier is a waveform, so while the output of the rectifier rises, the capacitor charges, and while the output of the rectifier declines, the capacitor discharges. and in that way smooth the DC output. Signal filtering is another application example of capacitors. Because of their specific response time, they are able to block low frequency signals while allowing higher frequency to pass through. This is used in radio receivers for tuning out undesired frequencies and in crossover circuits inside speakers for separating the low frequencies for the subwoofer and the higher frequencies for the tweeter. Another rather obvious use of capacitors is for energy storage and supply. Although they can store considerably lower energy compared to the same size battery, their lifespan is much better and they are capable of delivering energy much faster, which makes them more suitable for applications where high burst of power is needed. So that would be all for this tutorial, but you can always find more. At this point, the capacitor is actually...
So at this point, why isn't the charge here going back here? Because now all the negative charges are there. Why is it that they're staying there and not being shot back to the other plate? Mark, what do you think? Exactly. Yeah, so this battery is able to repulse it. Why aren't there more electrons going here? Because assuming you didn't take every single electron, why isn't any more going? Why did it stop at this point? Yep. Yeah, so now there is repulsion on both sides. So it's being repulsed by this and it's repulsed by going the other way. Also, another way of looking at it is there is a capacity of these parallel plates. Remember, we talked about capacitance. That's defined by the area of this, the voltage here, what's in the middle. So this is the capacity of this capacitor. Now, what's also really important for the question that we were doing before
Actually fully charged.
Mute this. When we unplugged it, there we go. Okay, so we unplugged it. Unplugged. All right, no more voltage source. Why is it staying the way that it is? Margo? Yeah, so these electrons have nowhere to go, because if they go here, they're just going to fall out. No, that's not how electricity works, so they're going to stay there. There is no closed circuit, right? If I didn't have a dielectric here, what would happen? Shadi? How? Like this? Or jumping across the plate? Yeah, they would jump. So if there wasn't an insulator here, and there was a conductor such as air. Air is a conductor because it's got water molecules in it. If there was air there, then the electrons would be able to jump across here, and you would discharge your capacitor by doing that. All right, and that's not what you want. You want this to stay differently charged, so that when you plug it into something else later, so something that doesn't have repulsion, such as in this case this tiny little light. I'm just gonna wait for it to show up. There it is. Right? So now that there is this tiny little light, these things are going to want to come back this way because there's a complete circuit, and therefore there's an access for them to go towards the positive end of this capacitor. And by doing so, they pass by this light, and when they pass by this light, they light up the light, or they do some amount of work. Okay, does that make sense? So let's go back to that question and see if we can get an answer for it. So here it is. So is this the right one? Okay, so if we're back here, if the capacitor was disconnected from the battery before the dielectric was inserted, what would happen to, one, the amount of charges? So what would happen? It would stay the same. So the charges would remain on the parallel plates and they would not move. Yep. What do you mean? Exactly. Yeah. But there is some dielectric, whether it's air or something else, there's something in between them, assuming that they cannot jump from one end to the other. Yeah. Exactly. It's just the more charge you put in, they'll have a higher chance of it discharging through the middle space. Rowan? But it doesn't matter whether there is a good dielectric or a crappy dielectric. The point is that there is some space in between them. And if you assume that they don't jump across, the charges would stay put. Every capacitor is going to have a different configuration. So it depends on, so if you have a capacitor, has a certain capacitance, if you go above that capacitance, then it's going to start jumping or start doing something unpredictable. Or with any dielectric, everything has a capacity, right? So let's say you put the most amazing dielectric in there. At a certain point, you're still filling up the plates to its maximum capacity. And if you try to go above that, it's going to jump across. Okay, so the amount of charges, they stay put. And now the second question is, what's the voltage? That's a hard one. I'm going to bring back just that picture in that video. If I go to that video. So before, they were using a, let's say it was a 1.5 volt battery. What would be the voltage now, once you disconnect the battery, what would be the voltage across these two plates? Rowan? Bigger? If they don't jump across, it shouldn't be bigger, it should be the same, right? So the charge per second, like the discharge time, that's going to be bigger. So you're going to get a big shock if you touch this versus if you touch a battery. But the voltage across it is going to be the same. So if you use a 1.5 volt battery, it's going to be the same voltage. So in the PowerPoint here, you can say that the voltage doesn't change. Yeah. Yep, give me 1 second. So the voltage adopts the voltage of the power source that it got it from. So it becomes, so the amount of energy potential that was used to send those electrons there means that those electrons have the same potential to go back. Right? So if you remove the battery, that has the same potential to go backwards. Therefore, it's got the same voltage. Okay. The same voltage as power source. Power source. And the amount of charges stays put. All right. Finally, I have one more video for you. It's that that lady that I showed up before. Again, this one here, I implore you to watch it on your own at home as well, because she's gonna talk fast. It's gonna test your ability to do English. Let's see how you guys are up for the challenge. Even I have a hard time understanding how fast you go. What's that? Her English is pretty good. It's just, it's her speed.
You've probably seen it on TV a bunch of times. A person collapses in a hospital and the doctor rushes over with a couple of paddles, puts them on the patient's chest, and then shouts, "Clear!" After a jolt, the patient is saved. That life-saving technology is real, and it works because of two main electrical principles: electric potential energy and capacitance. Those paddles are parts of a defibrillator, which is basically just a really big capacitor. It uses electric charge to store energy, which is then discharged into the patient's body. The current stops the irregular contractions of the cardiac muscle and gives the heart a chance to start beating normally. Get ready, because this lesson has the potential to save lives. To understand how a capacitor can save someone's life, let's review what capacitors are and how they work. A capacitor consists of two parallel conductive plates of opposite charge with an electric field between them. This setup allows a capacitor to store energy as electric potential energy. In the same way that an object has gravitational potential energy when you hold it above the ground, a charged object can have electric potential energy when it's held in an electric field. And in either case, potential energy can be used to perform work when a force is applied over a distance. But how can you determine how much electric potential energy a system has and how much work it can do. Like in the case of a defibrillator, you just want enough potential energy to stop an irregular heartbeat, but not so much that it causes harm. To measure potential energy in an electric field, let's imagine a positive test charge that's moving between a capacitor's plates. When we place the positive charge between the plates, the uniform electric field generates a constant force on it in the direction of the negative plate. If the test charge starts on the positive plate and travels in the direction of the electric force, we can calculate the work done on it by multiplying the electric force by the distance between the plates. We also know that this force is equal to the value of the test charge times the electric field. We can apply an equal and opposite force to the charged particle and move it across the capacitor as slowly as we like, so that the kinetic energy of the particle is negligible. And because of what we know about the work energy theorem and the law of conservation of energy, we know that a change of potential energy is equal to the work done by the external force or the negative work done by the electric force. So we found the potential energy decrease of a single point charge in a uniform electric field. And this drop in potential energy divided by the test charge magnitude gives us the electric potential energy difference per unit charge, also known as the electric potential. The electric potential depends on the electric field and the position, but it does not depend on the charge of the test charge. Now, the units of electric potential are joules over coulombs, more commonly known as volts. And the electric potential difference is also called voltage, which is another way of describing a drop in electric potential. When we express it mathematically, voltage is equal to the negative electric field times the distance between the capacitor plates. Okay, we've used our hypothetical positive test charge to describe how much voltage is present across the charged capacitor. Now let's put our new expressions to the test and find the electric potential difference in a real scenario. Let's say we have a capacitor with plates 1 millimeter apart and an electric field of 1000 newtons per coulomb, which is the same as 1000 volts per meter. The electric field can be found by dividing force by charge, or for that matter, newtons over coulombs, as well as voltage over distance or volts per meter. They all represent the same value. So say we multiply 1000 volts per meter by 1 millimeter, we find that the capacitor has a voltage of 1 volt. Now, since a capacitor creates a uniform electric field, we can assume the electric force is constant and that it acts in the direction in which the test charge moves. And as it moves, the potential will decrease more and more. We can represent this voltage drop visually by drawing lines along the locations where all the test charges have the same voltage. These are known as equipotential lines. In a capacitor, these lines run parallel to the plates, and each line that's closer to the negative plate has a lower electric potential or a lower voltage. And these equipotential lines are always perpendicular to the electric field. So far, we've learned how to calculate electric potential for capacitors, but can we apply the same ideas to point charges? Well, we know the equation for the electric field generated by a point charge, but since there's no uniform field like there would be with a capacitor, we can't use all the equations that we've been using so far. Finding the electric potential created by a point charge is like finding the difference in potential energy per unit charge between the spot right next to the point charge and somewhere infinitely far away. If a small charged object with the same sign was next to our point charge Q, it would start with a high electric potential while it was close by and have a very low electric potential as it got farther away. So we can calculate the total electric potential possible by integrating the negative electric field from infinity to 0. We're left with an equation that describes the electric potential generated by any point charge. And we can map equipotential lines for point charges in the same way we did for the capacitor. For a point charge, the equipotential lines look like circles of increasing size around the charged particle. The farther away from the point charge, the lower the voltage. And for an electric dipole, which is one positive point charge and one negative point charge, the electric potentials from individual charges can be added together. Here you'll see that each equipotential line is not a constant distance from a point charge. That's because you've got 2 point charges with their own electric fields. So a test charge on the right side of the positive point charge won't have the same potential as one the same distance away on the opposite side. Now let's go back to potential energy in capacitors, because it's largely why capacitors are so incredibly useful. From defibrillators to electronic components, when a capacitor's plates store electric charge, they're actually storing energy. If you connect a battery to a basic circuit that contains only a capacitor, the battery causes charge to move from one plate to the other through a conductive wire. This results in one positively charged plate and one negatively charged plate. But the capacitor hasn't gained any net charge. There's just as much positive charge on the positive plate as there is negative charge on the negative one. So the battery uses its own electric potential to generate a current that transfers voltage in the battery to voltage in the capacitor, giving the capacitor a certain amount of potential energy. For our defibrillator, this energy is quickly turned from potential energy into a jolt of electricity through the human body. Now, if you're trying to save a life, you want to make sure you're getting just the right amount of energy out of the capacitor. So to measure measure how much charge a capacitor can store, we can use a battery in our circuit to create a voltage between the plates and then divide the charge in each plate by that voltage. This value is known as capacitance, how much charge a capacitor is able to hold. Capacitance uses units of farads, with 1 farad equal to 1 coulomb per volt. Typically, capacitance values are very small, so we often talk about capacitors in terms of microfarads or nanofarads. And capacitance is actually determined by the size and shape of a capacitor. One way to express capacitance is to divide the area of each plate by the distance between them and multiply that by a constant known as the permittivity of free space, denoted by epsilon naught. Make the plates larger or move them closer together, then there's room to fit more charge, creating a stronger electric field. And once you've established the geometry of the plates, the capacitance does not change, unless you stick something between them, which actually increases the capacitance. And this something is called a dielectric, typically an insulating material like plastic or glass. A dielectric is used to increase capacitance while preventing any charge from jumping from plate to plate. Sometimes as the plates get hotter or the voltage gets higher, some electrons naturally jump between the plates, decreasing the amount of stored charge. So an insulator prevents electrons from crossing the gap. And you usually want the plates to be as close together as possible without touching, since a smaller distance equals a larger capacitance. So by using a very thin dielectric, the distance is decreased while the plates remain separate. And the molecules that make up dielectrics are polar, which means one side of the molecule is slightly positive while the other side is slightly negative. The molecules align themselves with the electric field and generate their own field in the opposite direction, resulting in an overall weaker electric field while the plates retain the same amount of charge. So by inserting an insulating material into our capacitor, we've increased capacitance and can hold more charge and thus energy for the same amount of voltage. And that's why the full equation for capacitance includes a dielectric constant K. So dielectrics can help capacitors hold even more energy, and that potential energy is actually stored within the electric field between the capacitor's charged plates. We can calculate the potential energy stored in this field by integrating the voltage over the charge in the plates, which reduces down to 1/2 charge times voltage. But when using a capacitor, it's useful to know how much energy is stored in an electric field per unit volume. We often want to know how much energy is in a certain location, like between capacitor plates. So we use energy density, or the amount of energy stored in the electric field, per unit volume. And we can calculate the energy density associated with an electric field at any point in space by dividing the potential energy by the volume between the plates. With some algebra, we find that this boils down to 1/2 epsilon naught times the electric field squared. And this relation holds true for any space with an electric field. Now that we know all this, a medic can make sure those defibrillator paddles have the right capacitance, have been given enough charge to create a high voltage, and then clear! Physics to the rescue. Today we learned a lot. We talked about electric potential energy and how it differs from electric potential or voltage. We discussed how capacitors function and the factors that determine how much charge they hold. We also learned how to maximize energy storage and how to calculate the potential energy held by any capacitor. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check
Yeah. I tried doing that in my office, and it just sounds really weird to the point you won't be able to, like, here, I'll just try a sample of it. So even at, let's say, 0.75.
capacitor, giving the capacitor a certain amount of potential energy. For our defibrillator, this energy is quickly turned from potential energy into a jolt of electricity through the human body.
To me, it's the, yeah, shiny. No. So the ones that you're responsible for are the ones in the notes. There is one that I will talk about later, and that's the energy stored by a capacitor, but we'll do that once we do circuits, capacitors and circuits. So that's the 1/2 QV squared, that one. Okay. Any other questions? All right, so let's take a small break, and then when we come back, we're going to do review for the test. So I have some questions prepared that we can work on together. I mean, I have enough to cover the whole hour that's left over, so it's really up to you guys. Do you want to take it up until, that's not the right time, eh? 30, so come back at 9:40, and we'll do questions up until the end. You mind just turning on the lights, Mike? Say that again. Okay. 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 You'd have to catch up somehow. It'll be like you're missing class for other reasons. So what you can do is you can listen to the videos. You can take notes from someone else's notes. You could try whatever. You'll have everything that's available to you that you've had so far, and it'll be up to you to kind of figure something out. So I've uploaded this to Moodle as well, so you have access to it. It's not a secret or anything like that. It might just have the wrong date on the front of that because it's the one from last year. I just modified it a tiny bit for this year. So I want you guys to do this. We'll try to do this. How should we do this? We'll do one together with me and then one on you guys on your own. We'll alternate that way, okay? So we'll do the first one together. I'll read the question. The solid inner shell holds a total of -3 nanocoulomb charges, while the outside sphere holds a surface charge distribution of whatever that sigma is. The inner radius is 3 centimeters. The outer radius is 10 centimeters. And the question is, hey, find the amount of charges on the outer shell. Okay, so that should be relatively easy. It says that it's uniformly charged, and it's got a charge density of sigma coulombs per meter squared. So if I multiply sigma by the area of the outer shell, then I should be able to find the charge. So Q is equal to sigma times area. So this is for A. Can you guys see my writing? It's to change colors. So A, Q is equal to sigma times A. And sigma is equal to 5.57 times 10 to the -8 coulombs per meter squared multiplied by the area of the outer shell. So how do I figure that out? What's the formula for an area of a sphere? 4 pi r squared, exactly. So 4 pi times the radius, the outer radius, which is 0.1 meters squared. All right. So if someone can do that on their calculator, let me know what you get. Yeah. Nope, this is the surface charge distribution of the outer shell. And you want to know the charge of the outer shell. No, no. Someone have an answer for me? Shani? Say that again. Okay, coulombs. All right, that makes sense. Yep, that makes sense. So there's my charge in the outer shell. So B, find the electric potential at a point located 2 centimeters away from the outer shell. Yep, Shani. Oh yeah, it tells you to find the number of charges. Yeah, so let's do that. So we have -7 times 10 to the -9 coulombs divided by 1.6 times 10 to the -19 coulombs per charge. And that's equal to should be something times 10 to the 10 or 11. .37 times 10 to the 10. 4, okay, I'm good with that. I can be more specific about my units, right? I wrote charges, But you can be more specific. What could you say instead of charges? You can, in this case, you can say electrons because you know it's negatively charged. So you wouldn't say negative that many electrons, you would just say that many electrons, okay? Can't have a negative number of charges. So B, find the electric potential 2 centimeters outside of the outer shell. How would you do that? This is tricky. I'll give you a hint. You have to use V is equal to KQ over R. Since you're outside of the outer shell, you can treat the shell as a point charge, which means that you could use this formula, right? You can use KQ over R. So we have K, which is 9 times 10 to the 9. We have Q, which is negative 7 times 10 to the negative 9. And what's R? Nani? Exactly. It's not just the distance from the surface of the spherical shell. It's if you're going to assume that that spherical shell is a point charge, then you have to go from the distance to the point charge in order to figure out the distance. So the outer radius is 10 centimeters. So it's 2 centimeters beyond the outer radius, which makes it 12 centimeters. So divided by 0.12 meters. Can you guys do that in your head? Let's see if I can. This times this is 50, 63 divided by 2. 63 times 8. About 500 volts or something like that. What's the answer? 8? Minus 525 volts. All right, C, sketch the electric field lines inside and outside. We've done this a lot, so this should be okay. So this inner radius thing has a negative charge, so everything on the inside is going to be going inwards. And the same thing for the outer charge, because the total net charge is negative plus negative, which makes it negative. So all of my electric field lines are going to be pointing towards the center of this. Shiny? It's K multiplied by Q, with the charge of the, you know what? No, what I didn't do actually, there's a mistake actually. I'm not supposed to do just the outer charge. I have to do the inner charge and the outer charge. So that's what I forgot to do. So let's go back to B. The Q is not just the outer charge. It's the inner charge as well. So what's the, it's 3 nanocoulombs and 7 nanocoulombs, which makes it negative 10 nanocoulombs. So negative 10, just change my color again. So negative 10 times 10 to the negative 9 coulombs divided by 0.12. So that should give you something like 700 something volts. Negative 10 because the inner sphere has negative 3 nanocoulombs. The outer sphere has negative 7 nanocoulombs. That gives me negative 10 nanocoulombs. So my answer should be closer to actually 800, something like that. So what answer is it? How much? 750? Negative 750 volts. Shani, that's still not what you got, though. Did you follow what I did? It's not squared. That's for potential. That's for electric field. All right, so back to my drawing here. All the electric field lines point inwards. Kind of looks like a bloodshot eye. Does everyone understand why it's pointing inwards at all points? Bronwyn? Because the distance, okay, so can I erase my electric field lines? Did everyone understand that they're all pointing inwards? Yeah? If the charge inside would be positive, it would look like this. The outside, if the outside is stronger than the inside, it's the outside that wins. Okay? It's whatever's strong. Like when you're on the outside, it's whatever's stronger that wins. Okay, so let me just answer Bronwyn's question. Now I'm having a hard time erasing these, of course. No. Okay, it's glitching, looking mad. Okay, I'll just do it this time. So here's your inner circle. Here's your outer circle. This has a radius of what? 3 centimeters. This has a radius of what? 10. So if you're 2 centimeters on the outside, then you're 12 centimeters from the inside. This radius is not 10 centimeters more than this one. It's the same center. So this and this share the same center. So this is 2 centimeters here. And therefore, this distance here is 12 centimeters. Because it's telling you that the surface, so in A, it's telling you that the surface density for the outer shell is sigma. And so you use the radius of the outer shell, which you did. You use 4 pi times r, which is 10 centimeters. No, even if we're a volume, the radius is still always from the beginning. Even if we're a volume, the radius is still from the beginning. Yeah, I guess in that case, if it were hollow or something. All right, so that's question 1. Good job, you survived. Question 2, this one you guys do on your own. So I'll try to solve it here, but I'm not talking it out loud. You guys do it on your own, try to figure it out. You need to think about this stuff. Hold on to it for now, yeah? All right, I'm going to move on to question 3. The answer, by the way, for question 2 is A. So question 3, two positive charges, or they are 8 microcoulomb and 2 microcoulomb, are separated by a distance of 300 meters. So I'm just going to draw that to make it easier for myself. There you go, 8 microcoulomb and 2 microcoulomb have a distance of 300 meters. A third charge is placed at a distance r from the 8 microcoulomb charge such a way that the resulting electric force on the third charge due to the other two charges is 0. The distance r is, all right, so I have to put a charge here, and this charge is how many? The third charge is placed, such a way that the resulting electric force is 0. The third charge, okay, doesn't tell you the charge. Okay, so it doesn't tell you the charge. I don't know if this is going to be possible. And we're asking you for what this distance are. How is this possible? You're saying it's between the two. That's not really clear though. So you're saying that Q is somewhere here, and this distance is R, therefore this distance is 300 minus R. And that if you add the forces from the two, so it would be 0 is equal to KQ multiplied by 8 times 10 to the negative 3 divided by R squared plus KQ multiplied by 2 times 10 to the minus 3 over 300 minus R squared is equal, oh, this has to be negative because they're going in opposite directions. And then you're solving for R. Oh, yeah, okay, we can do it this way. Thanks, Mark. So I set up my equation so that my two forces are equal to 0. I wrote down what I can. My Q's are going to cancel out because if you bring one to the other side, so let's do this algebraically. KQ multiplied by 2 times 10 to the negative 3, I'm bringing this over to this side, over 300 minus R is equal to KQ times 8 times 10 to the minus 3 over R squared. My KQ and my KQ, they cancel each other out. So I'm left with 2 times 10 to the minus 3 times R squared. I'm bringing this R squared over is equal to 300 times 8 times 10 to the negative 3 minus 300R. Yep, I brought this over like that. So I distributed the 300 minus R. Did I do it wrong? Ah, you're right. Yeah, you're right. I just squared it. So 300 minus R square is going to be 300, or 900 rather. 900 plus, plus, minus, minus 300R plus R square. Did I do that correctly? Yeah. that. And so then now I multiply. Yep. Is that good now? Okay. So now multiplied by 0.008. So 90,000. You're going to have to do the quadratic formula for this, right? Yep. That's true. Let's do that. Sounds more like, so if I keep it, it's 8 times 10 to the minus 3. I can square root both sides. What's the square root of? Okay. It's going to come out to be the same thing. Yeah. So let's square root both sides. So what's the square root of 2 times 10 to the negative 3? Can't do that much. 30 something. Zero point 0.45. And what's the square root of 8 times 10 to the negative 3? Like that? Okay. Now we're just solving for r. So you can divide both sides by, and you have to distribute it, right? So the 0.045 r is equal to 300 times 0.089 minus 0.089 r. And we'll bring that over to this side. Looks like I'm going to get a positive number. That's good. Very good. So r is going to be equal to? I'm sorry? 200 meters? Does anyone confirm? Yeah? Okay, so 200 meters. That means the distance here is 200 meters from the left charge. Makes sense? Interesting how you don't need to know the charge. Why is that? So regardless of which charge you put there, it doesn't matter because at that point the force is 0. Yeah. Where did I do this? Which step? I'm not following. Where? Which step? Here again? Okay. So let's think about this. Why is it that no matter which charge you put there, okay, so this is an interesting question. No matter which charge you put there, there is going to be no force on it. What does that mean? Yep. It's not that the other two cancel out. There is something going on at that point that no matter which charge you put on that point, the force is going to be equal to 0. So it has to do with one of the concepts that we learned that we talk about a lot. That concept is Magic? Kind of. Yep. But a force is always between two charges. So the charge Q is going to be one of the charges. So it's going to be the force between that Q and this charge. That Q and this charge is going to give you the same force as the same Q with this charge. So in either cases, you're using this Q. So the concept has to deal with, if we were to eliminate that Q from the equation, what does that leave us with? It's not force, but exactly. So that means the electric field at that point is zero. Essentially, that's what that means. So I'm going to write that here. Electric field is zero at R is equal to 200 centimeters, 200 meters. So the answer would be B. All right, question 4. This one you guys do on your own. I'll work it out over here. Uniformly positive charge sphere conductor is placed midway between two charge spheres. Hey, show how charges on the left and right space will be distributed space between them. So again, please work on this on your own. Don't look at my answers. How are the two objects on the sides being charged? What's that term called? Induction, yeah. Those of you who are doing the lab and you had this shape here, who had those shapes? That shape, yeah. So what ends up happening here is if you apply a negative charge here and a positive charge here, then you're going to get the positives coming in here, and that's going to affect the electric field lines. So you're going to have electric field lines that are going to go like this on this side, and like this on this side. In the middle is weird. Theoretically, it should go like this as well, but it's going to not be theoretical for sure. Yep. Yeah. So this is not the case because it's inductive. If I were like this, right? Now there is no, you can't induce something that's infinitely thin because the positive charges and the negative charges are still going to be on the line. So in this case, it's just going to go like that. That I remember. Do you remember the example? Can you show it to me after class? Okay, that was question 4. Let's do question 5. A non-uniform volume charge distribution for a non-conducting sphere of radius 2 is modeled by some rho as a function of r, where r is the distance from the center of the sphere. Calculate how many charges are held by the sphere. Oh boy, let's do some calculus. And calculate the electric potential at a distance of 3 centimeters from the sphere. So we have a sphere, and we know that the charge dq from one of the spherical shells inside is going to be equal to the charge density rho as a function of r multiplied by a small volume that I'm choosing. All right. So that would make my integration happen, right? So I'm going to do q is equal to the integral from 0 to r. I'll put in the r afterwards, multiplied by the charge density, which is 4r plus 3 coulombs per meters cubed, multiplied by the volume, which is 4 pi r squared dr. Yep, shiny. Yep. It's well, usually you write the constants as capital R, but I see that in this case in the question they wrote little r. So just to avoid confusion, I'm going to go do this. No, it's not. The 4r plus 3 and the 4 pi r squared, those r's are the radius of your small spherical shell on the inside. Volume. Let me explain. So 0 point. Right, so you guys say that I need to find out the volume of this shell here, right? The one I'm circling at the top, that one small thin shell. To find the volume of that one small thin shell, it's the surface area of the shell multiplied by its thickness. So the surface area of the shell multiplied by its thickness. Mark, does that answer your question? So if I take the constants out and everything, it's going to be Q is equal to 4 pi integral from 0 to 0 0.02. Make sure you convert it to meters because the charge density is measured in coulombs per meters cubed. If you don't change if you don't make the conversion, the math won't work. So this is going to be 4 pi r3 minus or plus 3 r2 dr, and that's equal to r to the 4. I forgot my 4 pi. R to the 4 minus r to the 3 from 0 to 0 0.02. Can someone evaluate that for me? You got it? What? What's that? 4r23? 4r to the, oh yeah, because it's 4r multiplied by r squared. I took the 4 pi and I put it out here as a constant. Melanie, do you have an answer? Cool. Yep. Oh, you're right, it is plus. Does that change anything? No. Okay. No, it's supposed to be plus. Yeah. It's supposed to be plus because it's plus here, and therefore it has to be plus there. I think what you're thinking of is you have to do the r of this minus the r of that. But, yeah. And B, calculate the electric potential voltage at a distance of 3 centimeters from the sphere. Well, that's easy. Now we just do V is equal to KQ over R. And that is going to be K, or 9.99 times 10 to the 9, multiplied by Q, which we just solved, is 1.025 times 10 to the minus 4 coulombs, divided by R, which is 3 centimeters from the surface of the sphere. So therefore, that means it's 5 centimeters from the center of the sphere. So that. You guys have an answer for this one? It should be about 1.8 times 10 to the minus 7, something like that. Is that what you guys got? 1 point something times 10 to the negative 7 times 10 to the power of 7. So we're good with that? Moving on, question 6. This one you guys do on your own. An electric dipole consists of a positive charge separated by a negative charge of the same magnitude by a small distance. Which, if any of the diagrams, best represents the electric field lines around an electric dipole? A dipole means that they're two opposite charges, and the two opposite charges will have a magnetic field, an electric field that looks kind of like that. If I were to ask you about the voltage, what would it look like? Would it be 3 or 2? If I asked you about voltage. 3. I'll tell you something. One of these represents two similar charges, and one of these represents opposite charges. So try to figure out which one belongs to which. So this is either opposite. It's either going to be opposite charges, or it's going to be similar charges. You think it's 2? So how do we go from electric field lines to equipotential lines? Perpendicular, right? So if I were to draw perpendicular lines from here, whoops, there you go. Okay, and if it were here, I would have to go like that. So Shanyu is correct. The answer is 3. So this would be the voltage for that same thing. All right, I think we have time for one more question. The following diagram shows equipotential lines in volts around 3 punctual charges. It's supposed to be punctual. Okay. Determine the sign of Q1, Q2, and Q3. Draw electric fields around the charges. An electron. Okay, we'll do A and B at the same time. So, when you're talking about Q2, because that's the closest to the top, are the voltage around it positive or negative? Positive. So this is going to be a positive charge. It's going to be positive Q. What about for Q1? Negative. And Q3? Negative. Okay, so there's my answer for A. Draw electric field lines around the charges. All right, so let's just do the ones around the charges. It's going to go like that. And these ones are going to go inside because they're negative. So I can start connecting some of them. So it should look something like that. The electron is moving from point A to point B. Now I'm lost now. So point A is negative 2 volts. I'm going to write that down. Point A is negative 2 volts. Oh, why is it purple? And point C is also negative 2 volts. How much work is done on the electron? Zero. Because remember that work is delta V over R. Nope, not delta V over R, delta V times R. And therefore it's 0. Because delta V is 0. Nope, my relationship is not wrong. It's delta V times Q, not R. But it doesn't make a difference because delta V is 0. All right, a proton is released at point C. Where will it accelerate? What do you guys think? Yep. To the, exactly, towards Q3. Identify a region of weak electric field. Where would that be? Yep. Yeah, around there would probably be pretty weak in the top right corner. Why? Is it the equipotential lines that we care about? There are less field lines. The field lines, not the equipotential lines. There's going to be equipotential lines everywhere. Lastly, identify a region of high electric potential. Where would that be? Yeah? Close to which charge? All of them. It says high electric, so very positive, would be probably around Q2. I'm going to write that here. I'll stop it here. There's a couple more questions for you guys to practice with. Just do that on your own. Next class on Friday, there's a lab. Please come on time, all right? This time you're doing a full lab report. Make sure you look at that document. Read the lab before coming to class, please. What's your question, Shani? Around Q2 because it's going to be the most positive.